Hello everyone, welcome to Chapter 5, Integration. Here we look at integration formula, the ones we already know related to power rule and the chain rule. And also we'll be looking at even and odd function integrals. So we'll use all these techniques to help us to use definite integrals to find net area as well as total area. And we'll also look at some applications where we wouldn't call it as net area. We would rather say in physics, we would say net displacement and total distance traveled, those kind of things. Okay, so let's take a look at it. So use a power rule, or use the power rule to integrate, and we are given integral 1 to 4 square root of t times 1 plus t dt. Now the thing is, this is definite integral, so we're going to learn to apply the limits of integration into it. But these techniques are true even for indefinite integrals. Okay, we've seen that before. So if for indefinite integrals, we would find the integration and then do the plus c. Here we'll go further. That's the reason why I'd like to show more of these definite integral examples. But we'll look at some of the indefinite ones as well, so you'll see a mix of these. Okay, a quick recall. You know that if you had integral u power n du, we did u power n plus 1 over n plus 1 plus c. I'm giving it in the indefinite integral format. Okay, so let's just remember this when we apply the rule here. And so what happens is we now rewrite this 1 to 4 square root of t plus t square root of t. I'm distributing it. Okay, but then when you see it as a square root, maybe you don't really see the power n as you see in u power n. So I'd like to write this as t power half plus t times t power half dt. The moment you write it like that, you can begin to apply rules of the exponents, because you have the t and the t power half. So this t has a power 1, right? So you add the powers. 1 and a half is 3 over 2. So you want to write that. Rewrite that as t power half plus t power 3 over 2 dt. And then you can apply the power rule because it's all simplified algebraically. So now it's time to apply calculus. So you could separate it like this, like t power half dt plus 1 over 4 t power 3 over 2 dt. But I'm just showing it to you here. In future, I will not be splitting it up like this. I'll be doing them in one go. Okay. All right, so this is going to be t power half plus 1 over half plus 1. And remember, you have the limits of integration. So 1 to 4 plus 3 over 2 plus 1 over 3 over 2 plus 1. Again, limits of integration 1 to 4. So when we do it in one shot, I prefer that because you don't have to iterate it twice. You just evaluate it for that one big expression. So again, just for that reason, in future, I will not be splitting them up like this. All right. So the bottom is half plus 1, which is 3 over 2. When you flip that, that becomes 2 over 3, t power 3 over 2. And the limits of integration is 1 to 4, plus this is going to be 5 over 2 in the bottom. That becomes 2 over 5. And that will be t power 5 over 2, 1 to 4. Now we evaluate top limit minus the bottom limit. For the first one, 2 over 5, these are constants, so they don't have to be affected by this. So that's going to be 4 power 5 over 2 minus 1 power 5 over 2. 2 over 3. Again, 4 power 3 over 2 is square root of 4, the whole cubed. Square root of 4 is 2. 2 cubed is 8. Minus 1 power anything is 1, so that's good. Plus 2 over 5. Same here. Square root of 4 power 5. Square root of 4 is 2. 2 power 5 is 32. Minus 1. Now it's pure algebra. simplify these two. The LCD is 15, so then you have all these big numbers there. If you do all the calculations in the background, you should get 256 over 15. And that will be the answer here, where you use the power rule technique to integrate. Let's quickly recall what we did with the net change theorem, right? So we can use the definite integral to find directly the net change. Okay. But then you can also use the definite integral and use the absolute value to find the total change. When I say change, I mean the total area or net area or net distance, total distance. So whatever be the context, we can do all that here using the definite integral. The only difference is that you throw in absolute value if you wanted the total, and you will keep it as it is if you wanted the net. Okay. And in this problem, suppose a car is moving due north, which is the positive direction, at 40 miles per hour between 2 p.m. and 4 p.m. Then the car moves south at 30 miles per hour between 4 p.m. and 5 p.m. We can graph this motion as this, all right? Because now you have the miles per hour, which is the unit for the rate, the speed. You know that we're not talking about the position of the car, we're talking about the velocity of the car. Therefore, you know that we have the v-axis. We don't have an s-axis, right? V-axis and the t-axis. So if I want to find the area under the curve, in this case, the curve are these rectangular boxes, the area under the curve for between 2 p.m. and 5 p.m., then it's basically this shaded region here, right? These two shaded regions, one above the x-axis, or in this case, the t-axis, and the one below the t-axis. But what does this area actually mean? What does this area represent? So in other words, if I'm asking about, talking about finding the area under the curve is a v function, right? Under the curve v of t, you know that the area under the curve would be the same as writing the integral of v of t, and we're going from 2 p.m. to 5 p.m. because that's where the action is, 2 to 5. And because the integration is, the variable is t, it's dt. Now if you look at this, you're taking the integral of velocity, So let's make a quick connection here. S of t is the position, right? And under differentiation, we said s prime of t, which is ds over dt, was v of t, isn't it? Derivative of the position gives us the velocity. Here we're doing the reverse. We are doing the integral of the velocity. So what do you think that will give us? So if you took the integral, let me show that here. Integral of ds over dt, I'm taking integral on both sides, okay? Forget about the limits of integration, just the integration itself. We know from fundamental theorem of calculus, the integral and the derivative will undo each other, so this basically gives us s of t. So in other words, integral of v of t is your position, is s of t. Position in this case would be the distance, right? Because the object, the car, moved a certain distance because of the velocity. So this is actually going to give us s of t from 2 to 5, right? And that is the approach. So in this case, the area, it sounds a little counterintuitive because I'm saying the area is actually the distance. But understand here in physics, it is beautiful in that you're talking about area to see it visually, but then you're talking about taking the integration of velocity, which actually gives us the distance, the position, the displacement. So when a position is changed, the change in that position is called the displacement. So technically, area under the curve is the displacement. Now, if we wanted net displacement, we'll keep it as it is. If we want total displacement or the total distance traveled, then we'll throw in the absolute value. And we're going to do that over here. So integral of 2 to 5 v of t dt will be, because you have the positive area and the negative area, right? We still will split it up. We won't be doing the absolute value though. So it's going to be 2 to 4 and then 4 to 5. We're going to split up this interval into two parts. So 2 to 4. And what do you think will be the information here? 2 to 4. Now this is the function, right? This horizontal line will be the function because we're talking about this as it's this horizontal line, but we're only looking at it between 2 and 4. So this horizontal line is v of t equals 40, right? Horizontal line is y equals that number. So that's what we have here. And likewise, this is also a horizontal line, and this is happening at negative 30. So this is v of t equals negative 30. So if I come down here, from 2 to 4, the horizontal line is 40. So I just have to say 40 dt plus integral 4 to 5 has a function that is negative 30 dt. It's a horizontal line, so there is no variable in it. There is nothing to vary. It's constant. So this is nothing but 40, pull out the constant, 2 to 4 dt minus 30 integral 4 to 5 dt. Integral of dt, is t. So 40 times t with its limits of integration minus 30. Here again, it's going to be t with its limit of integration, which is 4 to 5. So 40 times 4 minus 2, upper limit minus the lower limit. There's only a t, so it's easy substitution there. 5 minus 4. So this is going to be 40 times 2 minus 30 times 1. 80 minus 30, which is 50. Now notice again, we didn't do the absolute value. Therefore, this 50 corresponds to the net displacement. Okay, you'll hear me repeat this several times. Please bear with me because I'm trying to remind you over and over again that if you used definite integral directly, you get the net change, the net displacement. Now, if I want to find out the total displacement, okay, so that will be, anyway, coming back to this 50, let me quickly interpret this. So what this means is at 5 p.m., right, that's where the story ends, okay? At 5 p.m., it's a positive value, right? So you know that the car, the car is 50 miles north of its starting point. The positive value indicates that indicates a direction, the north direction. Now, if I want to find the total distance traveled, 2 to 5, I'm going to throw in the absolute value. You will still split the interval from 2 to 4 and 4 to 5, 40 dt plus integral 4 to 5, absolute value of negative 30 dt. So 40 integral 2 to 4, absolute value of 30 comes back as a plus negative, absolute value of negative 30 comes back as a plus 30, the 4 to 5 dt. So you know the drill, we just did that before. So I'm simply going to come back here and say it's going to be 40 times 2 plus the 30 times 1. That was the only change. So it's going to be 80 plus 30, which is 110. What does this mean? Because this is the total distance, doesn't matter if it in what direction it went, you can say between 2 p.m. and 5 p.m. the car traveled a total of 110 miles. Yeah. On the other hand, here it gave us the net displacement. So if you looked up and down, the net displacement came out to be 50. So in other words, net displacement may include both positive and negative values. And the velocity function basically accounts for the forward distance and the backward distance, right? That's the reason why we're accepting positive, negative. But to find the negative displacement, you want to integrate the velocity function over the interval. And for the total distance, it will always be positive because you're automatically taking the absolute value. So it should always be positive. And it only says that regardless of direction, we are talking about the total distance traveled. So net displacement may be positive or negative, but total distance would be always positive. Given a velocity function v of t equals 3t minus 5 in meters per second for a particle in motion from time t equals 0 to time t equals 3, obviously it's in seconds, find the net displacement of the particle. You can graph this, definitely. It's a line, right? Because it's 3t minus 5. It's a slanted line, slope of 3. The y-intercept is negative 5, 0, negative 5. And you're looking at this, this is going to be an indefinite line, but we are only looking between t equals 0 and t equals 3. So you can focus on just that portion and shade that region. And basically, you're trying to find the area of the shaded region. And because it is a question on net displacement, you have to consider the positive and the negative areas and keep the negative area negative, the area below the t-axis. So if I were to quickly sketch this, I can think of this as, there's negative 5, so I want it to go like this. Let that be negative 5. And t equals 0, and then 3 will be here. Okay. And so if I were to just focus on the shaded region, right, then it's going from 0 to 3. So the shaded region would be this portion. And when I plug in 3, let's see what happens. 3 times 3, 9, 9 minus 5, 4. So roughly, say 4 is somewhere here. That's where this will end, right? So I'll have to kind of shade it like this. So this is just sketching it, where this orange is v of t equals 3t minus 5. So this is the area under the curve, and again, the positive and the negative areas are added, and the net displacement is to be found. Because it's talking about velocity, this has to be the t-axis, and this has to be the v-axis, obviously. Therefore, the integral of v will give us the s, the displacement. Okay, so we go from, because we have this help here, you can go from, the help of the graph, that it's going to cross the t-axis at this point. We don't know what that point is, and we'll have to solve this to figure out what that point will be. And that's not difficult because the function itself is very simple. Okay, so because we're trying to find the net change, right, the net change or the net displacement, we really don't have to worry about the positive and the negative, and that's the advantage of using definite integral. So you can go all the way from 0 to 3. You don't have to break at this point, which would be, if you set this 3t minus 5 to 0, t will be 5 over 3, right? So that's this position, 5 over 3. You don't have to split this graph from 0 to 5 over 3 and 5 over 3 to 3. You go all the way from 0 to 3 because definite integral takes into account the net change. So it is really convenient in that sense that all you have to do is just this. So this time I'm going to integrate it the way it is, and I'm going to split it into several parts. So 3t dt will be 3t squared over 2, 0 to 3, minus 5 integral dt will be just the t, so 0 to 3. Yeah. So you can do it like this individually, or as I mentioned before, I'm doing them all together. So that will be 5t. And I put the bracket just to help us see that I'm evaluating the whole thing from 0 to 3. Cool. So 3 over 2, 3 squared, right, minus 5 times 3. So upper integral, upper limit, sorry, minus the lower limit. So 3 over 2 times 0 squared minus, let me get this off, 5 times 0. Upper limit minus the lower limit. That's going to be 3 cubed over 2, so 27 over 2 minus 15 minus 0. All right, so use the LCD, clean this up. You get negative 3 over 2. Simplify it, of course. And that is a negative value. This gives us the net displacement. And if I were to attach units to this, remember this is the distance, right? So it's going to be negative 3 over 2 meters because it's measured in meters per second. So negative 3 over 2 meters would be the net displacement of the particle. Okay. And again, as I mentioned previously, we do not have to split the interval to integrate over the positive area and the negative areas separately because they asked for the net displacement. If they did ask for total displacement, yes, you have to split it up and throw absolute value, especially for the negative area here. And then, as I mentioned before, it's better to throw absolute value in every piece because it doesn't hurt. But you know that this is a positive region, and so 5 over 3 to 3 would be the positive part. And so you'll get the total displacement, total distance in that case. If the motor on a motorboat is started at t equals 0 and the boat consumes gasoline at the rate of 5 minus t cubed gallons per hour, how much gasoline is used in the first 2 hours? So we're told the rate in which the gasoline is consumed, and we're asked to find how much the quantity of gasoline was used in the first 2 hours. And so if you were to express this problem, we would be doing this as a definite integral, right? And so our endpoints would be t equals 0 to what would be the other end? The other end would be the first 2 hours, it said, right? First 2 hours. So 0 to 2, that is our interest. And the function is 5 minus t cubed dt. And I'll go ahead and find integration on this. That's going to be 5t minus t power 4 over 4. And for this whole thing, we apply the limits of integration 0 to 2. So 5 times 2 minus 2 power 4 over 4. This is the top integral minus the bottom integral. Sorry, that's 0 power 4. The second one is a complete 0, so that's just the top one. So 10 minus 16 over 4, which is 4. So 10 minus 4 is 6. So then you can come back and say the motorboat, because the word problem you have to interpret it, uses 6. Now this is the amount of gasoline, so it is 6 gallons of gas in 2 hours. Then we have even and odd functions, and this is kind of a shortcut. Now we recall that if it's even function, you have the symmetry about the y-axis. That's what we learned in algebra. We also saw in algebra that, as well as in trading for that matter, that if you replaced your function, your variable x by a negative x, there was no change in the function. The function looked the same, right? On the other hand, for odd functions, we saw that the symmetry was about the origin. If for even functions, the symmetry was about the y-axis. Here, the symmetry was about the origin. So if you recall, we can say this one was like a parabola because the symmetry was about the y-axis. And for this, we can think of it as a chair-shaped graph where the symmetry is about the origin. Therefore, f of negative x is negative of f of x. Well, if we are talking about integration, remember we're talking about area under the curve. So if I'm going from negative a to a, so that's negative a to a, you know that because it's symmetry about the origin, if you just did 1/2, say you went from negative a to 0 or you went from 0 to a, if you just did 1/2, you can multiply that by 2 to get the total area. And that's what this first rule says. On the other hand, integration for an odd function from negative a to a would mean that you'll have equal and opposite areas, and so meaning positive and negative areas, so they will cancel each other, and that's how we get the 0. We saw that in one of the trig functions, right? The cosine example that we did last lecture or a couple of lectures ago. And so we have seen that before. Now we have a rule to help us with these even and odd functions. So if you recognize that they're even and odd, you just have to, it's easy for you to use the shortcut and find the area. Find the total distance traveled by a particle according to the velocity function v of t equals 3t minus 9 meters per second over the time interval 1 to 5. Very similar to one of the problems we did before. But they want us to find the total distance. Okay, so for that, we want to make sure that the total distance is positive areas added up, so which means you have to do the absolute value. Whenever they ask for total distance, we need to make sure that we split the interval at the t-intercepts. Usually use the x-intercepts, here it's called the t, so the t-intercepts. And how do we find the t-intercepts? This means you set your velocity to the function to 0, which is 3t minus 9 equals 0. Solve for t. T gives us 3. Right. When you look at this sketch, you can see that your velocity will be negative from 1 to 3. The velocity is positive, right, from 3 to 5. So if I were to split this up, so let me first write from 1 to 5 v of t dt, and because it's total distance, it's absolute value. I know that from 1 to 3, my velocity is negative, so it's negative v of t dt. And from 3 to 5, my velocity is positive dt. Okay, we put in absolute value, but I'm trying to see this. We are using the absolute value. I'm giving you another version of another view where absolute value is nothing but a piecewise function that collects the negative portion and the positive portion. So I'm taking this negative portion and I say negative of 3t minus 9 dt plus 3 to 5 positive version. So there is just 3t minus 9 dt. Okay. So what this does for us is from 1 to 3, if you distribute the negative, you actually get 9 minus 3t, the other way around. dt plus integral 3 to 5, 3t minus 9 dt. So it's 9t minus 3t squared over 2. 1 to 2. 3t squared over 2 minus 9t, 3 to 5. Notice that because we did the negative of vt and positive vt, we didn't have to do the absolute value because this will take care of it. In fact, you see that the reversal of the terms, right? 3t minus 9 with a negative reverses the sign, and therefore you have it as 9 minus 3t. This will take care of the resulting answer from being negative. Okay, top limit. So this is for the first one, 3 minus 1, okay, top limit minus the bottom limit, plus that's the first part, so 5 minus the 3. So just watch out, it can get a little confusing, but just stay on top of the terms. And as I always recommend, never try to skip steps or do things in your head. Try to write them out. Even if it looks complex like this, it doesn't matter. Put them out and then go ahead and simplify it. Anyway, I'm going to ask you to pause the video here and do the computation. We should get something like this. The top should give us a 6. and the second term, the plus, and then this term should also give you a 6. That will be 12 meters. Okay, obviously this is algebra, so I'm slowly, as I mentioned earlier, we are nearing the end of the course, so I'm slowly weaning you off of too many steps to show you the algebraic portion of it. I would like to concentrate more on the way we will deal or handle the calculus portion of it. Therefore, I want you to really get well versed in your algebraic techniques. Okay? A particle travels according to the velocity function v of t. It's given as a piecewise function. You have two pieces. They both are lines, as you can see, right? 2t minus 1 and negative 2t minus 1 and 2t minus 5. These are two lines. One has a negative slope, the other has a positive slope, so you can kind of see it. One going down and one rising. And it's happening over those specific domains. So you get a picture, you get an idea of what they're referring to as the velocity function. Where velocity is measured in meters per second, find the net displacement of the particle for the first 3 seconds. So a net displacement is what we're asked to find. And we know net displacement implies we use definite integral as is, right? Meaning we don't really split into intervals. That is our understanding so far. However, your v of t itself is split up because of the piecewise nature. Because of the split up, you do have to use these these domains as your intervals. So 0 to 1 would be this piece, and from 1 to 3 would be this piece. So even though we will use a definite integral as it is, we will have to do this. So 0 to 3 v of t dt has to be split from 0 to 1 v of t dt and 1 to 3 v of t dt. Notice that we're not doing a negative or a positive. We are definitely keeping them as it is. All right, so 0 to 1, the first piece was negative t minus 1, negative 2t minus 1, sorry, dt plus 1 to 3, 2t minus 5 dt. You know the drill now, so you can actually pause the video and meet me at the end of the answer. One to 3. Okay. And you know that these will simplify, right? The 2's will cancel off. So negative 1 squared minus 1 minus negative 0 squared minus 0. I'm writing it as it is. 3 squared minus 5 times through minus 1 squared minus 5 times 1. Yeah. All right. So now go ahead and clean up. So you'll get negative 2 for the first part plus this also will come out as negative 2. I did the calculation beforehand, so I want you to do the steps yourself. And that's negative 4. So you know that net displacement can be positive or negative. In this case, it comes out to be negative. So you'll say net displacement, as the question says, is found to be negative 4 meters. And remember again, you start with the velocity. So velocity is meters per second. The integral of a velocity will give you the distance. And in this case, the distance is measured in meters. All right, class, with that, we come to the end of the lecture. I hope you enjoyed it. It's a short one, isn't it? So in the next one, we will be looking at other methods, substitution method, and so on, to deal with integration. See you soon.